and welcome back, everybody. Today in calculus, we will be talking about section 5.4, which is on the definite and indefinite integrals. So at this point, we covered FTC1 and FTC2. And so we're now at a position where our lives are going to be a lot easier because we can find the area under the curve by using the antiderivative according to the second fundamental theorem of calculus. So that's what we're going to go ahead and discuss for today. So here, let me just kind of do like a quick recap then. The first part, what I'm going to talk about is that here, like I said earlier, if you're trying to find the area under the curve from A to B for f of x, FTC2, according to that, says that you just have to find the antiderivative and plug in the upper bound minus the lower bound, and then subtract one from the other. So here, the antiderivative is going to be represented as capital F of B, f of x. So then, as you can see, f of B, then capital F of B minus capital F of A is what I was referring to. So where capital F is supposed to be the antiderivative of the function that's given. Now, in terms of how does that relate with the indefinite integral and definite integral? Whenever somebody says that you are going to solve for the definite integral, that means you're literally solving for the area under the curve under using the FTC number 2. The answer for any kind of definite integral should always be a numerical value because it represents the area under the curve. Whereas if I ask you to solve for some sort of indefinite integral, then that literally just means solve for the antiderivative as a function then. So we'll get to see how each one of those actually work out for problems then. All right, so here we go. Let's go ahead and dive into some of these examples right here. So solve for the following. So you'll notice that for each one of these integrals, there is no boundary for the lower bound or the upper bound. So what that means is I just want you to solve for the antiderivative. So this is going to be an example of an indefinite integral, or both of these will be indefinite integral examples. So here's the first one then. I want to solve for the antiderivative of x times 1 plus 2 times x to the 4th. Well, if you go back to when we first introduced the idea of derivative and we only had the power rule to solve for it, here's the same thing. I don't know how to actually solve for the antiderivative if it were just given a form like this. So I think the best thing what we can do is just do the algebra and multiply it out. So x plus 2 times x to the 5th, because that is going to be my distributive property. And from that form, I know how to find the antiderivative. What function has a derivative of x? Well, I know it's going to be x squared. And then because the exponent is now 2, I am going to divide by 2 because, again, we're going backwards. We're not going to multiply by 2 because we're doing the opposite or the reverse of the power rule. Then for the second part, we have 2 times x to the 5th. So the antiderivative of x to the 5th is going to be x to the 6th. And just like before, what we're going to do is divide by 6. So then that means that you have 2 divided by 6 then. And for every single time that you do an indefinite integral, there should be a plus c at the end because c is supposed to be a constant. And if you take the derivative of a constant, it's always going to be 0. So what that means is that any kind of indefinite integral, there are infinite number of solutions depending on what c is, because c is really just where you're shifting the function then. So finally, just to clean this up a little bit, my final answer is 1/2 times x squared plus 1/3 multiplied by x to the 6th and then plus c. So that is going to be my answer for this indefinite integral. Okay. For the right-hand side, same idea. I want to solve for the antiderivative of 4 sine of theta minus 3 cosine of theta. So take it one step at a time. Now, this is where people get confused because sine and cosine, they're derivatives of each other. So we got to be very careful about how we're going to do this. So the first part is saying, hey, what function, when I take its derivative, is going to be sine? So then that means it's going to be negative cosine. Remember, we're taking the antiderivative, going backwards. The derivative of negative cosine should be sine, and then the 4 is just going to carry over. Then for the next part, the same thing. What function, when I take its derivative, will give me 3 cosine of theta? Well, that's going to be 3 sine of theta. Remember, we're not going forward, we're going backwards. Okay, so that's going to be minus 3 cosine theta, minus 3 sine theta. And then once again, just like before, there's going to be a plus c because we're just taking the antiderivative then. So there you go. Hopefully that example is not too bad for the indefinite integral. Now let's go ahead and talk about the definite integral, meaning where you're actually trying to find the area under the curve, where you're given boundaries. So this time around, we're going to go ahead and have to solve for it using FTC number 2. All right, so let's see how this works out. In the first case, I want to solve for the area under the curve for this function from 1 to 2. Now, we can graph it out if you want to, but I don't think it's really necessary in this case. And by the way, just for a technicality sake, on the bottom, we notice that y cannot equal to 0. So what that means is if your integral, right, if your integral right here, it contains 0, then that means I actually cannot solve for this antiderivative because it's undefined there. So just gotta, keep that in mind. But anyhow, let's go back to this over here. Just like in the first example, I didn't know how to solve for it when it's going to be in factored form. So over here, maybe what I can do is literally just divide through. So just using algebra once again before we do calculus, the integral from 1 to 2 of y divided by y, that's just 1, plus 5y to the 7th divided by y, that's going to be 5y to the 6th power. And then that dy is still going to be there. So this looks like it's something a little bit more approachable. So first what we're going to do is we're going to take the antiderivative. So that's going to be y plus y to the 7th power multiplied by 5 divided by 7. Okay, so that is my antiderivative. And this time now your integral becomes an integrand over here. I'm going to go ahead and write the 1 and the 2 to indicate that I'm supposed to plug them in to find the area under the curve. So like I said, according to FTC number 2, we're going to go ahead and plug in the upper number, and then afterward, take whatever that result is, minus it from the lower number. So the upper number plugged in, you're going to get 2 plus 5 divided by 7 multiplied by 2 to the 7th power. So that's the upper bound. Then I'm going to take 1 and plug it in and do the same thing. 1 plus 1 to the 7th power times 5/7, and that's going to be my lower bound. Take 1 and subtract the other. And right there, hopefully you can see that that's, like we said, capital F of B minus capital F of A. So we can just go ahead and clean this up, then we got our answers then. So usually what I do is I take the common terms and then combine them together because that's a lot easier to do. So 2 minus 1, that is equal to 1. And then the other part, which is going to be 5/7 of 2/7, and then 1 to the 7th of 5/7, that is going to be equal to, let's see if I can do a little bit of math on the side. They both have 5/7 together, which we can factor out. So that's 2 to the 7th minus 1. So again, the answer is going to be 1 plus 5/7 multiplied by 2 to the 7th power. Oh dear, what does that equal to? I think it's 128, I think. So 128 minus 1. Hopefully I didn't do that incorrectly. So now it looks like it's 1 plus 5/7 multiplied by 127 then. Okay, so we can go ahead and clean it up, or you could throw it into the calculator, whatever works best for you. Okay. All right, now the second part, we'll do exactly the same thing. Okay, first we're going to go ahead and take the antiderivative of it. So it's going to be 2 times e to the x, because remember, e to the x, the antiderivative or derivative is always going to be itself, plus 4 multiplied by the sine of x, because that's the antiderivative of 4 cosine of x. Then we're going to go ahead and plug in the boundaries, the upper bound again minus the lower bound. So plugging 5 into the equation, we're going to get 2 times e to the 5th power, and then plus 4 multiplied by the sine of 5. Then we have minus the lower bound plugged in. It's going to be 2 times e to the 0 power multiplied by 4 times the sine of 0. So fortunately, sine of 0, that is supposed to be equal to 0. Actually, wait, I think I messed up over here. This is supposed to be a plus sign over here. But nonetheless, 4 times sine of 0 is going to be equal to 0. So that kind of works out nicely. So now again, just looking at my like terms, let's see. We have 2 times e to the 5th, 2 times e to the 0. So that's like saying 2 times e to the 5th minus e to the 0. And then we have plus 4 times the sine of 5, and 4 times the sine of 0 is going to be gone. So final answer is 2 times e to the 5th minus 1, and then plus 4 times the sine of 5. And it could be the case where I can multiply it out, but I think I'm just going to go ahead and leave it in this answer because I do like it in factored form. All right. Now, let's look at this next one over here. I want to solve for the area under the curve from -3 to 2 of 1 over y. Now, this is where it gets dangerous because if you remember what I said earlier, in this case, I cannot actually solve for this. And the reason is, if you graph out what is 1 over y looks like, it's going to look like this right here. I'm asking for you to solve for the area under the curve from -3 to 2. And that's impossible because this area under the curve, notice that it's undefined at 0. So while it is symmetric for the equation of 1 over y, because of that discontinuity, we actually just say we can't solve for it. So the answer for this is actually does not exist because y simply cannot equal to 0. And remember, y is in that interval that we were talking about. But let's just say for the sake of technicality, I want to solve for something like this where I can solve for it. Let's go ahead and solve for the following then. Let's go ahead and say the integral from -3 to -1 of 1 over y dy. Okay. Now, in this case, we can solve for it because it's continuous everywhere from -3 to -1. And now we're going to go ahead and take the antiderivative. What function has a derivative of 1 over y? Well, that is supposed to be the ln of y. But this is going to be a little bit strange because ln of y, if you recall, looks like the following. This is supposed to be the ln of y. How do we compensate for the antiderivative of the left-hand side if we have 1 over y then? Meaning, like, if you look at the antiderivative, there is literally nothing that's on the left. So in order to compensate for that, we do the following. We actually say that the absolute value of y, the ln of absolute value of y, is going to be my antiderivative. Because if you look at the graph of absolute value of ln of x, or ln of y in this case, the graph is going to look like this, the symmetric part about the y-axis. So now you actually have two parts on the left and on the right where you can actually find their derivative. And the derivative of each case right here, if I draw it out, then you can see that it's actually going to be, oops, using a wrong pen, it's just going to be, like we said, 1 over x then in this case. Okay, so in conclusion, over here, let me just kind of write this on the side, and you're going to definitely need it from here on out. The integral of 1 over y dy, or 1 over x dx, I think that might be a little bit better for you because you guys are used to using x, is going to be equal to the absolute value of x inside the ln, and then we have plus c. Okay, so this is something that we're going to be needing. That's how we're going to take care of the negative part. So going back to our original question right here, right? Here's my antiderivative, and now we're going to go ahead and plug in the upper bound and the lower bound. Now, like I said, normally if those boundaries are positive number, no problem at all. But if they're negative numbers, well, this is where that absolute value comes in. So my answer is going to be ln of absolute value of -1 minus ln of absolute value of -3. So once you take care of the negative part with the absolute value, well, that comes out nicer. That's ln of 1 minus ln of 3. ln of 1 is equal to 0. So then that means the negative ln of 3, that's going to be my answer. And that is the area under the curve from -3 all the way to -1. So that's this portion over here. Okay. All right. Now let's look at these final two questions over here. And these are a little bit more, well, we wouldn't be able to solve for the antiderivative. So there must be some sort of trick to this. Well, technically the first one you can solve for the antiderivative, but you'll notice that, well, you'll see what I mean by the trick, okay? Let's go ahead and plug in what we have over here. Try to solve for the antiderivative as you would normally, the area under the curve using the definite integral. So first of all, the antiderivative of x to the 2/5, that is going to be x raised to the power of 7/5 because it's the reverse power rule. Then I'm going to multiply by 5 over 7 because we multiply by the reciprocal, right? Because, again, reverse power rule. And then we say plus x because that's the antiderivative of 1. And now we're going to go ahead and plug in the boundaries from -32 to +32. Well, if we were to plug everything in, then the upper bound will give me the following. 5/7 multiplied by 32 raised to the power of 7/5 and then plus 32. That's the upper bound. Minus the lower bound, which is going to be 5/7 multiplied by -32 raised to the power of 7/5 and then minus 32. Okay, a lot of extra algebra right here, but we can definitely deal with it. Let's see if we can kind of clean this up. we have 5, 7 multiplied by 32 raised to the 7/5 minus negative 32 raised to the 7/5. Again, what I'm doing is I'm basically taking the like terms and combining them, which is this guy and this guy right there. So that will give me this piece over here. Then we have the second part, which is going to be plus 32 minus 32. So that's going to be plus 32 over there. Okay. Keep cleaning it up. 5/7 multiplied by, if it helps, 32. I can write it as 2 to the 5th power. And then we have 7/5. And then minus, this was going to be negative 2 to the 5th power raised to the power of 7/5 also. And then plus 32 plus 32 is equal to 64. This is where the 5th and the 5th root cancels out. 5th and the 5th root cancels out. So 5/7 multiplied by 2 to the 7th minus negative 2 to the 7th, and then plus 64. And as a result, that is going to give me now 5/7 multiplied by 128 plus 128, and then plus 64 then, which is then equal to whatever the following answer is. 5/7 multiplied by 2, so let's go ahead and make the 10/7 times 128 plus 64. Kind of nasty. Now, here's what I want you to notice about this problem over here, okay? If we were to graph this, and let me just go show you what the graph looks like. We're going to go to decimals over here. Let's see, it took a little while to load, but it's okay. Y is equal to x raised to the power of 2 divided by 5, and then we have plus 1. Notice the graph right here is symmetric about the y-axis. My boundary, keep in mind, is from negative 32 to positive 32. So what that means is if the left-hand side and the right-hand side look exactly the same, why do I make this integral a lot easier for myself by doing the following? Instead, this problem right here, I can rewrite it as the following instead. This is going to be the same thing as the integral from 0 to 32 of x to the 2/5 plus 1 dx, and then multiply by 2. And if you can solve for that integral, you should get exactly the same answer. But the difference between doing this integral that I just introduced and the integral that I did over here is that the 0 plugging in is a lot easier than the 0 than having to plug in 32 and negative 32. So for that reason, we want to make our integral a lot easier, and maybe using something like this would actually work out. So this technique right here only works for symmetric equations. That is to say, even equations, where f of negative x is equal to f of x. If you recall, this is what is known as an even function. So we can always do it for that one. Now, if you remember, there's something called an odd function as well, where the odd function has the following property. F of negative x equals to f of x to the negative outside. And this is what's happening for this second case over here. Now, if I were to graph this out, let me see, let's see what that looks like, okay? So once again, we're going to go back to decimal. I'm going to clear this out. So y is equal to, I think it was sine of x. Oops, not that. Sine of x. And then we're going to go ahead and divide by 1 plus e to the power of, erase this, x power of square. Okay. So a little bit hard to see, but you can see now what's happening in this case is that we do actually have a symmetry, but the symmetry over here is about the x-axis and the y-axis, and hence that's why it's an odd function. Well, looking at how the graph is shaped right here and how the left-hand side looks like the right-hand side, but the negative of it, if I were to ask you for the area under the curve, one would say so long as the left-hand side is symmetric to the right-hand side, the answer would be equal to 0. So here you can see, like say, for example, if I ask you for what is the area under curve from -1 to 1, you would say it's equal to 0 because what's above the curve, what's above the x-axis is the same as what's below the x-axis, but one is negative, the other is positive, hence that's why it's 0. So going back to our question over here, right, the area underneath the curve from -a to a of sine of x over 1 plus e to the x squared, because we have an odd function, we can actually go ahead and say the answer is just straight up equal to 0. And that means that I don't even have to solve for what is the antiderivative, because I don't even know what the antiderivative of that guy is. So in conclusion, if you take a look at the equation and you see the symmetry of negative a to a, negative 32 to 32, and then you have some nasty looking function, one might say, hey, there might be an easier way to solve for this. And maybe this is where this trick of making a double from 0 to some number, the even function then comes in. Or maybe it's just the area is equal to 0 and there's no work. All right, well, thank you so much for watching, and I will see you guys next time. Have a good one. Goodbye.